This is a presentation of PowerPoint 3, Making Programs Fail, done by our members Vlad, Leonard, Walter, and myself. Now, testing can be broken down into two phases: testing for validation and testing for debugging. Testing for validation seeks to find unknown bugs not apparent in the development process. This may be done with the use of play testers, the release of a beta version, or even feedback after the product has gone to market. As the program is distributed into the production-like environment, the bugs become apparent to the user and are reported to the development staff. Now, most proprietary software is tested in-house by taking a few users out of production and placing them in a safe testing environment, reminiscent of a honeypot and challenge to break the program they work with every day. In this way, the known unknowns become known. Now, testing for debugging is concerned with known bugs and how to fix them. Once a bug is known, there must be a way to test possible solutions in the most efficient way possible. Stress testing can often isolate network or hardware issues. Automation through the use of macro programs can simulate user interaction and quickly test the known issue. Output must be verified to ensure a proper solution has been derived. Multiple runs should, in most occasions, it should produce the same result. Isolating these problems saves time, and there is no need to migrate or move your data if the issue is confined to computation. Here we have an example of a Mozilla problem report. Now in this report, when you simplify it into debugging purposes, a bug must be reproducible. This example shows the procedures to reproduce a known bug possibly submitted by a user. Automation through scripts or macros accelerate our ability to test these issues by eliminating redundant steps. Console commands will be easily automated through scripts, and macro programs can be implemented to exactly follow the above instructions. Once a possible fix has been applied, automation has been kicked off to attempt to reproduce the error. Now, after we reach something along the lines of this screen, it becomes important to manufacture these same conditions required to reproduce the failure. Some issues may be time sensitive or resource dependent. This may require, for example, the hard coding of a normally randomized integer or a line change specifically designed to cause conflict. Whatever the conditions required for the bug must be recreated so the bug can be observed and treated. This can even include some hardware specifications. Now, the challenges in the use of automation include compatibility and synchronization. See, the program must be able to interact with the software as a user would, simulating mouse clicks, keystrokes, and even biometrics sometimes. We'll also have to consider lag. Lag is a big hurdle when radio buttons do not load in the expected time or screens do not display the expected options. Macros must allow for this lag and anticipate that some of the conditions might not be ideal. Abstraction would be the concept of cross-platform integration, where we take the source code and we break it down into machine code, and that gives a situation where the code is ideally integrable across multiple platforms. Portability also refers to this ability where we're also doing the same thing. We are accessing this code across multiple platforms. Let's talk about the interaction layers. At the presentation layer, the user interacts with the software or hardware. This is where buttons are pushed and mouses are clicked. The functionality layer is where the program does its work by accessing and manipulating data behind the scenes. The unit layer, this divides up the program into distinct sections that can be tested individually. For example, a network or an individual resource allocation. Now, accessing these layers, we have to think about the ease of execution. We have to consider, can the program be run by a command line script? Does it require focus within the GUI? Is a tape mount required? Literally accessing the program and activating its functionality is covered here. Think about ease of interaction. We have to ask ourselves, does the program require mouse or keyboard events? Is touchscreen activity required? Things of this nature. And then we have to think about the ease of result assessment. Is the output a single or simple integer that can be checked as correct output or incorrect output? Or does this output in detail require a more thorough analysis? How easy or difficult it is to analyze program output is handled at this layer. And when you talk about the presentation layer, you have these levels here. In the presentation layer, low-level interaction includes mouse clicks and keyboard events, such as those handled by a script. High-level interaction involves a GUI and is generally the domain of macro programs. The difference between the low and high levels is generally defined by the sophistication of the macro or script language. System level handles the way different OS environments interact with the program. Use of virtual machines to simulate different system setups is used to test this level. Low-level interaction includes scripts such as BAT files or mouse and keyboard events that are captured and replayed when desired. This incorporates stress testing with predetermined or random input values. Here we have an example of an Android script. It's basically going to be used to make Mozilla Print in this example. Small changes to the screen layout or even the subtle changes in mouse position may cause these scripts to error out. Cats walking on keyboards is a common error seen here for all those cat lovers out there. Now, when we talk about system level interaction, we know that at this level, tests are designed towards specific systems in mind. Does this program work on Unix? What about Mac? What about Windows? Maybe on mainframe? Here we might have to use virtual machines to simulate certain system environments. When we move to higher level interaction, we have an example of AppleScript, which makes the same action of Mozilla Print. AppleScript on Mac OS is an example of one of our higher level scripts. It interacts with Mozilla and demonstrates how scripts can be specialized to a specific GUI. Some scripting languages. So AppleScript we have here, it can send or receive Apple events from applications, as well as being able to handle and process basic processing capabilities. We have JavaScript, which is a event-driven object-oriented language. It's used primarily in a net content aspect. We have VBScript, of course, for Microsoft, using Visual Basic. We have Perl, a Unix scripting language. It was originally developed for reporting, but it became popular in some CGI processing recently. Perl is considered basically kind of like a Swiss Army chainsaw of the development world, actually. And we have Python as well. Big open source language, of course. It has lots of benefits, many drawbacks as well, but it entails a lot of powerful scripting tools. Now, dealing with output. Testing output is paramount to good development. Essentially, the output is our reason for doing this entirely. Synchronization becomes an issue here, where processing must be completed before the testing mechanism can verify the output. Often, processing must complete before the output can be verified, and the testing mechanism needs a way to verify this. In most cases, a timing mechanism is sufficient. However, circumstances vary. When you talk about the functionality there, it, in essence, bypasses the GUI or the GUI completely. Why would we sit here and simulate mouse clicking when we just simply send a command which achieves the same result? The greater accessibility is offset, however, by the introduction of backdoors, which may be exploited by hackers of malintent, perhaps. These automated processes are sometimes easily exploitable. I'm not going to mention any names, but take a look at the picture. It'll speak for itself. Now, unit tests. Now suppose when your program fails when attempting to write its output to the server, it doesn't necessarily make sense to continue testing the entire program code when you know the program fails at a certain point. Isolating this procedure and finding the fault is a function of unit tests. If an error can be removed from the code and tested individually, then do so. In unit testing, simplification minimizes confusion. When it comes to running them, we have to think about the setup. We have to create a testing environment which encompasses all the processes that we will be needing. Sample data and other inputs that may be needed also need to be thought about. When it comes to the test should work on every possible behavior, and then it should be able to verify the correct outputs. Once we finish the test part, we go to step 3 of tearing down the environment. We must reset the environment simply to the starting state so that we can start back from step 1. On this slide, we have an example for a testing script for the Java language. This testing script is highly successful, and its approach has been adopted by many other languages such as C++, CPP Unit, VBScript, and a couple of more. Another one we have here, a unit test. This one is Python based. Of course, we mentioned that it was an open source. Take a look into these couple of lines of code of how the Python scripting works. Now, if you think about our testing environment, our testing environment is separated from a production, yet it's also holding the same schema, giving it the possibility to be a good test bed for our unit testing. A good test bed should mirror the functionality of our production environment and provide us an efficient way to test individual units with the same output as if it were run in production. When it comes to unit testing, oftentimes we have to break circular dependency. You see, safeguards have been put in place to prevent user error or to notify the user of special events. Certain safeguards and programs we create every day can also be roadblocks when it comes to testing our software. A common example is the file overwrite notification seen often in certain programs. Pausing every execution to click the OK button can significantly slow down our testing pace. Now, if we break this dependency, the program can be rewritten to a special test version that avoids this step. Take a look at this example on this slide, where the circular dependence is broken when we take an abstract superclass and we take another subclass to break that dependency. Now, when developing your program code in its totality, it is very important to keep debugging in mind. Making a target for low coupling prevents the need to later modify the code so that it can be tested. The more a unit can be separated from its peers, the easier it will be to test it after development is nearing completion. A good program is usually always designed for debugging where you can test each individual unit without significant or major modification. In this slide, we have a model view controller. This basically untangles our functionality and presentation at the application level. Now, the model is independent of the user interface. The model controls and protects the data, managing the actual functionality of the program. This is the display of data to the user. It can be in the forms of charts, graphs, or text. Now, the controller, its usual job is to accept the commands from the user and pass them to the model or view as needed. These are some general design rules. These terms simply separate units into those that are dependent on each other and those that are more on the independent side. High cohesion requires more development and possibly a separate environment, while low coupling, for example, operates almost independently of each other and can be tested with little changes to decouple. Slide here, we have some tools for our automated testing. We already mentioned some of these: JUnit, Android we saw earlier, AppleScript, VBScript. Other scripting languages we did mention Python and Perl, FAU Machine. Some of you might be aware of these tools already. VMware and Virtual PC. We do want to also mention that there's another software called Oracle VM VirtualBox, which is also a free virtual machine. It's most comparable to VMware on this slide.